Hey everybody, welcome back to another fun and exciting pre-calculus class. Today we will be jumping into lesson 3.3. Just like last lesson, there's no way to teach this lesson in one video, so I'm going to be breaking this lesson up into at least two videos, and it's possible we have to go to a third video. So lots to talk about in this lesson. Go ahead and open up your book to page number 41 and lesson 3.3. You'll see that it says we're going to be talking about arc length, linear velocity, and angular velocity. You might be thinking, this sounds more like a physics class. You're right. We're basically talking about physics information, but we're going to base it off of the circle. And so we want to kind of talk about it here so that you know how to do it. And a lot of these topics are going to kind of be, it's the line's just a little bit blurry between pre-calculus and physics sometimes, because you need both of them to understand the other one. So from geometry and the length of the arc S and its central angle theta are related to the circumference of a circle C by the equation S over C equals theta over 360. And you might think it's been a long time since geometry, so let's go ahead and look over here and let's talk about what that formula actually means. So what it says is that the arc length is S. So whenever you see S in this formula, this is arc length. Well, what is arc length? Well, we have a circle. The arc length is the piece that we're looking for, okay? So in this case, this would be the arc length. Let's say this is A and this is B. We want to know what arc AB equals, okay? This is our question. Okay, so we're looking for the S. This is going to be called the S, the arc length. All right. The formula says that it is related to the circumference of the circle. What does that mean? Well, it's related to the circumference of the circle, or it's related to the entire distance all the way around the circle. So this piece right here is related to the whole circle. All right, as theta, what's theta? As theta, this is theta right here. Okay, your arc right here is your theta. As this angle right here is related to the entire angle, to the circle, to the 360. Okay, well that makes sense, right? Because this theta is subtending this arc. And so the 360, if you talk about the 360 degrees, then we're talking about the whole circle. So 360 is related to the whole circle, like theta is related to the arc length. So that's your formula to find arc length. Now, jumping back over to the book, what they say here is they say, well, what about in radians? Can we put that formula into radians? Can we deal with that? Well, notice it says using 360 degrees equals 2 pi, which it does, because you memorized that from the last chapter, right? The last lesson. And circumference equals 2 pi r. What's 2 pi r? Well, that's the formula for circumference. The circumference of a circle, the formula is 2 pi r. And then that's going to give you, we're going to simplify, blah, blah, blah. Let's jump back over to the other screen and let's kind of do this. Let's actually simplify this formula into radians. All right, so if we want to get S, that one doesn't change because it's just the arc length. That one doesn't have any radians in it. Circumference, we change it into its formula. So now you have S over 2 pi r. That's the formula. Notice we're in radians all of a sudden. Okay? You didn't know we were in radians when you learned that formula back in 8th grade, but we are. We're in radians with that formula. Equals theta. That's our angle, so we're just going to keep that theta because we don't know what that is. That's just a variable. Over 360. Well, what is 360 in radians? Because we're going to transform that into radians, and that is 2 pi. Okay? So now what we want to do is we want to get S equals. We want to get this S by itself. I'm not going to take the time to break down the whole thing, but in essence, what happens is these two cancel once we move it over to the other side. Those two cancel, and we end up with S equals theta R. Okay, or R. I think they do it in the book R theta. It doesn't really matter since it's multiplication, but R theta, not R to the theta. That kind of looks like R to the theta. R times theta. Okay, what is R? It's the radius of the circle. Okay, so if we want to find the arc length, all we have to do is take the radius times your theta. That's it. Where did all this other stuff go? Where'd those pi? They canceled out. All right. So it's just the way that the formula works out. This is actually a very easy formula to use. Once you kind of break down the parts and once you transfer it over into radians, it becomes pretty easy to work with. All right. So now let's go back to the book. This is the circle that we're going to use, but let's go back over here to the book and let's look at example number 1. Example number 1, 3 students are on a merry-go-round. Now, when I was a kid, many years ago, there was a thing called the merry-go-round on the playground. I don't think I've seen a merry-go-round on a playground for years. Why? Because kids would get hurt on it, and there'd be liability, and, nowadays you can't have anything going on that's a little too crazy at school, so it's a little bit more tame on the playground. So, what is a merry-go-round? Let's jump back over here. Let me try to explain this to you just a little bit. In the center of the merry-go-round, right here, there's like a pole that goes into the ground, and the merry-go-round is like a disc that sits on that pole. Well, here on the outside, they had all of these little like metal bars that you would hold on to, okay? Every so often, there'd be a metal bar. All right, let's just put one more. All right, and it's not balanced, but whatever. And you'd have one kid standing out here, okay? And he's actually a giant kid, because the merry-go-round's pretty big. But anyways, they got the giant kid standing out there. And so the giant kid would grab that merry-go-round and they'd spin it. And the thing would just rotate on that center point and just keep going around in circles. Well, the whole thing would be going around in a circle, okay? Whichever way you wanted to push it. So you could go either way on the merry-go-round. And it would just sit and rotate on that center point, and it'd just keep going around and around and around. And the bigger the kid, this guy is right here, the more muscle that kid's got, the faster he can get that merry-go-round going. And I mean, we got it going so fast at times where you could like hold on to this bar and you just be like holding on for dear life, and your legs would be like flailing out from the merry-go-round, and you'd just be whipping around in a circle. Okay, that's why they got rid of them, because of people like me on the playground that would, abuse the merry-go-round. It's supposed to be a nice little ride. Maybe you've seen carousels at circuses and fairs and things like that. It's kind of a similar idea, but it's all manpower in this one. One person standing out there, or multiple people. You could have multiple people whipping the people around in a circle. All right, so now you know what a merry-go-round is. Let's go back to the book and let's talk about this problem. 3 students are on a merry-go-round. So there's 3 people on the merry-go-round. Not the guy pushing it. 3 of them on the merry-go-round. One is at the center of the merry-go-round, and the other is 1 meter and 2 meters from the center. Find the distance each travels after 90 degrees of rotation. So coming back over here to our merry-go-round, this is the idea. So we have one person in the center of the merry-go-round. Okay, then 1 meter, you have another person. Okay, and if you haven't noticed already, I am an amazing artist, just so you know. Okay, and so this is 1 meter, and then another meter, we've got another person on the merry-go-round. Okay, so this is another meter. So altogether, these two are, this is 2 meters. All right. So they're all holding on at different spaces on the merry-go-round. Well, if you can imagine, this middle person is just spinning around in a circle. They're not traveling any distance. They're just spinning on the very center. So that pole is just spinning in there. And I used to love being in the middle of that merry-go-round because you would just spin and spin, and then you get off it and you couldn't stand up because you were all dizzy, and you'd fall over. But that's the person at the middle. Now, this person here is going around kind of this circle right here, right? Okay, so it's like an inner circle that person. The middle person is just spinning, right there in the middle. Then this outside person is spinning kind of on the outside of the merry-go-round. Okay? Now, think about it. Is the middle person moving? Now, they're just spinning in a circle. They're not making any distance, not traveling. Okay? Now, here's what the question is asking for. They're saying in a 90 degree, and I'm going to erase some of this in a second, but so this is a 90 degree angle right here. How much distance does this person right here travel to get to this point? How much distance did they move on the merry-go-round? This little piece right here. What does that equal? Then it wants to know how much does this person travel out here, because they're traveling different distances because they're traveling around a larger radius of the circle. Okay, so let's erase some of this so we can see it again. All right, so now let's talk about the middle person. Well, the middle person doesn't travel. And let's talk about that mathematically. What does that look like? Let's go back up to our formula. Here's our formula. Okay, and now we have to convert it to radians. And so we end up with this formula right here. We end up with S. What's S? The arc length. How far are they traveling? That's the S. That's what we're looking for. And we need R times theta. So we go back over here and we say S. Let's call this S0. The S0 is the center guy. He's the one at the center of the circle. We could call it whatever. We'll call it S0, the center guy. He is traveling what? What's the radius of the circle? There's no radius, it's just a point. He's just circling around a point. So there's 0 radius. So 0 times theta. What's our theta? Well, our theta is our 90 degree angle, because that's what the problem says. The problem says 90 degrees. So our theta is 90. Well, what is 0 times 90? So the distance traveled by person 0 at the center is 0 meters. They don't travel. Okay, and so we'll put it over here. S0 equals 0. That person did not travel. They didn't make any movement. Okay, so let's go to the next one. S1. We'll call this person 1 right here. Okay, so we'll call this 1 meter. This will be the 1 meter person. Okay, so this is person 0 meter, and this is person 2 meter over here. So the 1 meter person. Now, what is our radius now? What is our R? Well, on this one, our R is 1 because our circle radius right here is 1 meter. Okay, so we have to do 1 times 90 degrees, or in other words, person 1 or person 1 meter, the person at 1 meter out travels what? Well, they travel, and you say 1 times 90, so they travel 90. No. We have a problem. On this one, on the 0 one, it didn't matter, but on this one, we can't use 90, can we? Okay, why not? What does our formula tell us? Our formula tells us that we have to be in radians. Okay, so come down here, and we have to convert this 90 to radians. So we'll call it 1 times, what is 90 in radians? Well, if you memorized your chart, you would know that it's pi over 2. Remember, we're in radians now. So what do? Well, we're going to multiply this. So 1 over 1, we'll multiply the fraction, and we're going to get S1 equals pi over 2. Well, now what you need to do is you need to multiply that out on your calculator. You need to divide pi by 2. So I'm going to take my calculator, and I'm going to, on mine, it's shift and then this key. So I'm going to hit shift and then this key here, that's going to be my pi, and I'm going to divide it by 2 and hit equals. This is where everybody's calculator is just a little bit different. Mine gives me my answer in radians still, so in fraction, basically. It did not multiply this. Why? Because this is a more accurate answer than in a decimal. But when we're dealing with feet and meters and measurements, we want a number. We want it to be, we don't want pi involved in our answer. So what we want to do here is, and your calculator works different. Yours might not have given you a fractional answer. What I have to do is I have to go down here and hit S to D. Basically, I want a decimal answer. So I'm going to go ahead and hit that, and I'm going to get 1.57. And I could round that off to 1.6. Okay, so my travel for person that's 1 meter away is going to be 1.6. 1.6. Now we want to find the person that's 2 meters away. How far are they traveling? And this would be in meters. So the first person travels 0 meters. The second person travels 1.6 meters. And then the third person, how far did they travel? So let's get rid of some of this. I'll leave some of these things on here where we converted to pi. I'll leave that, or to radians. So this is person 2. Now, notice that person 2 is, for the radius, they are 2 meters away. So we have to do 2 times this. Well, what happens now? Well, that cancels and we get 1 times pi, or we get just pi. So what is the answer? Well, it's just pi, 3.14. So you could do 3.1 meters. All right, now I want to go back and I want to show you something. On each one of these right here, we put equals. On this first one, you could leave equals because we did get a definitive 0 times anything always equals 0. So we could leave that 0, but on these ones, we had to round off. We did not get an exact answer. Now, if we left it in pi, it was exact, but we don't want to leave it in terms of pi because we're dealing with length. So what we want to do here is we want to put our little squiggly line, our little bacon lines, to let everybody know that we're rounding those off. Those are rounded off measurements rather than exact measurements. You can look at that in your book as well. You can see that their steps that they used and how to solve that out. But that's really the first part of the lesson that I really want to talk about, is how to use this formula, how to convert it into radians so that you get the arc length equals the radius times your theta. Okay, there's some practice problems there that correspond with that first part, with that first example, so you can work on those, and then make sure to watch the second part of the video where I continue to talk about the different things on the following page, on page 42. Okay, all right, that's all I got for you in this lesson. We'll see you later. Bye-bye.